So the next speaker is Tuomas Virtanen. Tuomas got his PhD, master's and PhD from Tampere University of Technology, where he is now a research fellow and associate professor. And he's leading the audio research group. Most of you know Tuomas from his great work on application of NMF to music signal processing and robust speech processing. So, and he's going to talk today about hiding about sound event detection in realistic environments. So, using DNNs.
Thank you, Jonathan, and thanks to the organizers for the possibility to present here. I don't have audio from my computer yet, so. Should be plugged in, right? I don't see any. There is a problem on your side. Right. Okay. Okay. While these guys are setting the audio up, I guess I can get started with my talk. So I think many of us here are interested in developing methods, computational methods that analyze audio signals. And okay. Great, good, thanks. And since there's so much stuff done on okay, should be full screen coming. Okay, since there is so much stuff done on speech and music, then I figure out that maybe why don't I take this smallest goal and try to deal with all the rest of the sounds. And okay, so I have quite ambitious goals too. I mean, what if we deal with all the sounds in everyday environments, like human-produced non-speech sounds, footsteps, coughing, laughing, yelling, and cars, machines, beeps, animals, and so on. And of course, there is plenty of sounds in everyday environments. So basically, the approach that I'm taking is kind of divide and conquer approach. And try to estimate the individual events from each of the sources. So that's what sound event detection means. Okay. So I will define first a bit more technically what is sound event detection, and for those of you that are not that familiar with the field, I will give some possible applications of this work. And then there's plenty of scientific and technical challenges. I will describe those. And then this specific DNN-based approach and some previous work to put the work in the context. And I will also introduce this coming challenge related to acoustic event detection. Okay, so the goal in sound event detection or acoustic event detection is that we estimate start and end times of acoustic events for an audio signal and give a textual label for each event. So in this figure, for example, okay, we have here these blobs showing estimated sound events. And you have the start and end times for each of those, and then label for each of them. And like you see from this figure, then there can be multiple events at a time. And also, I mean, of course, you have to define what are these labels in advance. So those would be called classes. And of course, you can turn this problem the other way around and basically do consider one class at a time and detect when that class is active. That would be an alternative definition. And okay, I have here a video which shows possible events from one specific environment. Okay, now how should let me see if I'm able to. It's so small here that I can't really see it from. Okay, let me use the QuickTime player. Maybe this is. Can you turn up the volume a bit? Okay, the events in this example, they were generated manually. But this is just to give an idea what kind of events we might be looking for. And okay, why are we doing this? There's plenty of applications. So for example, we can develop assistive tools for those that cannot hear sounds or cannot remember them. Different kinds of devices, robots, cars, mobile phones can recognize sounds in their surroundings and become context aware. For example, for a car, it's useful to know that there is some children yelling coming from behind a corner, and then the car can warn the driver, or if it's autonomous, then slow down. We can develop intelligent surveillance systems that, for example, detect the burglars in your home. And we can analyze human activity in urban areas or animal activity. I mean, apparently, urban designers are interested in knowing what people are doing and where. And similarly, biologists are interested in knowing what kind of animals are in certain locations. We can do some intelligent noise monitoring. And of course, guys in these buildings might be interested in using these technologies for multimedia information retrieval. So if you can, for example, automatically analyze sound events in all the YouTube videos, and then you can apparently develop better search engines. Okay, there is plenty of scientific challenges in this work. Of course, in realistic everyday environments, there is plenty of different types of sounds having very different acoustic characteristics. So this makes the design of detection systems challenging. So there is short transient time sounds. On the other hand, some sounds that are much more longer. So what kind of classification or detection architecture you would be using? What kind of acoustic features? And even in one class of sounds, then there can be very high acoustic diversity. And on the other hand, there can be two sounds that are acoustically very similar, but have different meaning, have different semantics. And okay, on top of that, in realistic environments, there is multiple sound sources that are often active simultaneously, and there is reverberation. So how do we detect then overlapping sounds? Also, there is no established taxonomy for sound events. So nobody telling us what are the classes that should be used. And also, we don't have such huge databases that the ASR people have. And of course, that's a difficulty in the development. Okay, so to put this DNN work to the context, then I will show some a bit older work. And okay, most of the results that I'm showing are with this kind of CASAR computational audio scene analysis corpus that we have which consists of recordings from 10 different contexts: basketball match, beach, public bus, car, hallway, office, street, restaurant, shop, street, and stadium. And we have about 20 hours of annotated material from these contexts. So we had actually research assistants marking the start and end times of sound events in these recordings. And we had a procedure where they were first using free textual labels to characterize the events, and then afterwards we're grouping these to 61 event classes. So in total there is like 10,000 annotated events in this database. Okay, let me illustrate this data a bit. You get an idea. Okay, where's the cursor? Okay. Can we have a bit louder? Okay, so it's data like this from for example, this is from the street context, and so there is also a video that the annotators were using to help the annotation process. But we are mostly in our work we are not using the video. I'm collaborating with the machine vision guys that use also the video, but I've been working mostly with the audio. And then we have annotations like this, basically similar to the figure I was showing earlier. So we have here a number of classes, and for each of the classes we have these blobs showing the start and end times of the events. And okay, this shows an histogram and list of some of the event classes that we have there. For example, there's the applause class, so that's present in the track and field sport event and the basketball match. Then we have ball hitting floor. Guess what? It's present in the basketball game context. And then beeps are present in shop. There is the cash register and in the bus, and so on. And okay, I will be showing some results. So of course we want to use some metrics here. So here we are using F-score in 1 second blocks. So for the ground truth or the annotations, we are checking if an event is active within 1 second blocks, and similarly for the system output, and we are then calculating the number of true positives and negatives and so on, and getting the F-score, average F-score over the whole database. And this 1 second segment resolution is used simply because in case of many of the annotations, it's a bit ambiguous when event starts exactly or when does it end exactly. So then it does not make sense highly accurate temporal resolution for the evaluation. Okay, so we actually started this in around 2009, and then at that time we didn't really have those DNNs yet. GMM HMMs were the established technique. So we started with simple GMM HMMs, and for each class just a 3-state HMM. So we had training data. Okay, we had some 5-fold cross-validation setup and training, validation, and test data. And okay, for training we then take all the annotated instances of each event class and simply use the EM algorithm to train the HMM for each of the classes. And then for modeling longer signals, we simply combine these individual event HMMs. This kind of network of events where any event can follow any other event. And then we simply do feature decoding to find the most likely state path in this kind of network, and so this gives us an alignment between the time frames and the classes, and we can directly use the output to detect when events are active. So for example here, now this event class C is active starting here and ending there, and we get output like this. So this output is monophonic, meaning that there is one system is outputting only one event at a time. The most prominent event, I guess. And okay, so this the performance of this system is 15% F-score. So this is indeed F-score. This is not error rate. So it's not really doing that great job. And okay, obviously one of the limitations there is that the system detects, this kind of system detects only the most prominent event at the time. In practice, in this data and realistic environments, we have multiple sounds at the same time. For example, in this CASA database, we calculate the average number of events at each time, and that's 2.5. So that's the average polyphony. So we are missing many overlapping events with this monophonic system. And we have had several attempts how to deal with now this polyphony. And okay, one very simple trick is to actually run the Viterbi algorithm multiple times. So run it once, then exclude those state and time combinations that were found during the first round, and then run the Viterbi again. You get then multiple paths like this, and then you get events from all these paths. And okay, then you get a slightly better result, 20% F-score. Now the limitation with this, both these approaches is that we still are extracting features from the mixture signal that consists of multiple sounds. And okay, in that case, if we have acoustic models for individual classes, then of course there is a mismatch. And my group has been doing quite a lot of work on sound source separation, so of course we wanted to give it a try. And what is good in the case of acoustic events is that they have relatively stationary spectral structure. So, for example, car sound is rather stationary typically, and many transient sounds can be also modeled with rather simple NMF models. And we first try out unsupervised NMF. So simply separate the mixture signal in multiple streams, and then you run this GMM HMM recognizer on each of the streams. And okay, we are able to almost double the F-score using this kind of approach. That's nice. And okay, now one fundamental limitation in developing sound event detection systems is that for many types of sounds, it's very difficult to get sounds in isolation. For example, if you consider some car engine sounds, so you would need you cannot really take the car into your audio lab and record it there, but there's typically some background noise always. Okay, and our training material is from realistic environments, so there is also overlapping sounds there. And okay, then we tried doing the same unsupervised separation for the training material, and actually then we came up with a clever EM algorithm to select which of the separated tracks corresponds to which of the sources. And okay, that improves the results even better. Now, it took us a while to figure out how to actually do source separation and recognition simultaneously or jointly, and then actually pretty nice way to do this is with coupled NMF, where you have your acoustic feature matrix, and at training stage you have your acoustic feature matrix over there, and then you have a annotation matrix, which is basically binary matrix telling when each of the classes is active. Then you simply factorize this data. Then you get some dictionary atoms that jointly represent the acoustic features and the event activities. And then you get the excitation matrix that represent the temporal activity, each of the dictionary atoms. And when you do testing, you have the acoustic information only. You factorize it using the acoustic part of the dictionary. you get the excitations, and then this way you get the same excitations to multiply with the activity part of the dictionary, and then you get the estimation of the class activities. And okay, that works even better, so 58% F-score. Now, all these systems here, they are context dependent, meaning that we take training material from one of the contexts, train a classifier using material only from that context, and test using the same context. And okay, if you do it this in context independent manner, so if you don't know what is the context at test time, then the performance of these methods is slightly lower. Especially the NMF method seems to be in trouble if you make it context independent. And okay, then towards this DNN-based approach. So then in this work we actually then don't use source separation. So because that's somewhat tricky. Source separation always produces some artifacts, and then we wanted to try out what if you recognize sounds from the mixture signals directly. So the basic paradigm is that we have here these, we have our acoustic data and annotations, and then we simply encode the activity of each of the events, this multi-label encoding. So this is a binary vector where 1 means that an event is active and 0 means that it is not active. And what if you simply try to predict activities like this? And there is one, when we use this multi-label classification approach, trying to predict the presence of all the classes at the same time, there is then the potential that the classifier actually can figure out the relationship between the classes. So we are not detecting classes individually, but all the classes at the same time. So the classifier has the potential actually to learn correlations between classes and even priors. So if certain events seem to be jointly active, then the classifier has the potential to learn this kind of relationships, and also the acoustic relationship. So the classification part is actually rather easy. So we have audio, we extract features, and that's our input to the DNN. And then we have the annotations of our acoustic event. We use this multi-label encoding. So this is basically binary metrics telling when sounds are active or not. And that's our target output. And then we have simply a DNN learning the mapping from the acoustic features to this activity labels. And at the test time, okay, surprise, surprise, we extract acoustic features, input to the DNN, then we get the source presence or class presence probabilities. We do some post-processing, and then we get the activities of each of the classes. Okay, so let's zoom in a bit. So actually then the features and the DNN part is much more simpler than what we use here. I mean, I will first represent the simple feed-forward net approach. So as features, we such used local energies, 40 bands, 50 millisecond windows, and 50% overlap. And we modeled the local temporal context by concatenating features from 5 adjacent frames. And the DNN is actually, okay, does not need to be that deep. And I think one of the limitations is that we don't really have that huge databases. So it's like 20 hours of audio. Okay, we have tried more than up to 5 layers or something like that. But the improvement is not really that much. So only with 2 layers we are doing quite okay. And 800 hidden neurons, and we use max out activation function with 2 neurons pooling the max out. And since we are doing multi-label classification, we can have multiple events active at the time. So we cannot use softmax output, but we use logistic sigmoid. And then we simply use for the output, we use threshold 0.5 to decide if an event is active or not. And for the training, we use standard cross-entropy cost and stochastic gradient. And okay, so the output post-processing is a simple 10-point running median. We have some work on some combining the DNN with an HMM, but the results that I'm showing are very simple running median filter to get rid of some peaks in the output. Okay, and now this system gives us 60% F-score. But what is notable is that now this system is context independent. So it doesn't need to know from which context your data is coming from. And it seems to generalize much better to contexts that are not in the training set. So let me show some demonstration. Okay. Okay, so first of all, the data that we have here is rather noisy. So it's, for example, here is mostly detecting that there is some traffic every now and then. Okay, now most of the recordings that we have are stationary, so there's no person walking. But here, for example, there is some walking, and then, of course, the system every now and then detects that there are some footsteps. I will show some. There are some quite interesting things if we switch to some other context. For example, here to this SOP context. So let's see over there. Where is the video? Okay, over there. I don't have audio. Okay, now. So for example here, let's move a bit forward. So now this is from a SOP. There is, you really can't hear it well, but there is some background music, and the system is detecting that correctly. Some humming coming from those refrigerators. And now then when the guy goes to the to pay, then there are some beeps from the cash register. It's again very difficult to hear them. But okay, if you listen to headphones, then the system is actually doing pretty good job in locating those beeps. But what is actually interesting here that if I visualize the annotations at the same time. So okay, let's move on. Okay, now you heard some beeps there. So the system is detecting them correctly. But now the annotation is this orange bar over there. So actually then the annotators were lazy. They did not mark those individual beeps, but just this very long sequence there. And, so the DNN is actually doing better job than the annotators here. And we are getting phenomena like this also in other contexts. So if we switch to restaurant, for example, here. Okay, again. Okay, we don't have video. This is not that advanced visualizer, but okay, this is from a student restaurant. There is, okay, now we have the video as well. So there is a lady in the foreground and talking to somebody. I cannot play this because of privacy issues, but okay, so the system is detecting that there is speech, and but actually also here, then if I switch on the annotations, so now the speech has been annotated to be active continuously. But actually when the person makes some short pauses, then the DNN system is clever enough to say that, okay, there is no speech. So again, it's doing better than the annotations. So, but of course now there is so the system is doing better job than the annotations. So, but obviously then, according to the metrics that we are using, then this is slightly problematic. Okay, and we actually have some. Ron was advertising LSTMs, so of course we have tried them as well. So if we try out multilabel bidirectional long short-term memory network, so this is actually more deep. We had something like 4 or 5 layers. Then we get even improvement to this, so the F-score is 65%. So this is our ICAS subsystem. I'm not going to tell all the details, so that let's see if you have the opportunity to hear that at ICASP next spring. But I think here already this, okay, 60% or 65% may seem not that great, but partly I think this is because the annotations. So somehow, because the annotations are subjective, and I think partly we are now saturating because even if our system is improving, then it doesn't really match with the annotations anymore. So this is one of the problems in the development of these methods. Okay, some discussion to wrap this up. Okay, so sound event detection is a new research field with plenty of interesting applications. There is, of course, I mean, I was showing results on one database only, but of course there are very diverse tasks. For example, if you are doing some burglar detection, then you have really rare events. You don't have that often burglars coming to your home. Or on the other hand, then the data that I was having is quite dense, so about 20, there can be like 20 events per minute. And of course, in some scenarios, you're interested in one class only, whereas there are then, I don't think there is no upper limit for the number of classes if you really want to get highly detailed descriptions. And, but what is great here is that we can use the same technologies in real-time systems, embedded devices, but also use the same type of DNA algorithms, for example, to analyze the content of multimedia collections, offline analysis of multimedia collections. And naturally, you can use various capture devices. So, I mean, the results that I was showing, it was one channel only. But naturally, if you have a microphone array, you can take benefit of the spatial information, or if you can have some acoustic sensor networks to localize sounds even better. What is good here is that you can borrow plenty of techniques from speech recognition, music analysis, use the same features, classifiers, so that makes it easy. On the other hand, there are some major differences to speech analysis, for example. So the taxonomy, what are the sound event classes, that's of course completely different from speech. So the atomic units are very different from speech. And like I was explaining, in realistic environments, we have multiple sounds at the time, so really polyphonic material. And also then the acoustic of sound events are very different from speech. So you have transient sounds, but also much more longer sounds. And there are really some fundamental challenges, like what are the classes that you should be using? There is no established way how those should be defined. And we don't have really that big databases that ASR researchers have. And manual annotation is really time-consuming. And the annotations are subjective, like I was explaining. So in the case of some events, like transient types of sounds, it can be relatively easy to define what is the exact onset and offset. But for example, if there is a car passing by, when does the sound exactly start? When does it end? Difficult to define. And also, how do you measure the performance of your system? Okay, and this multi-label approach seems to be pretty good. So at least we were able to beat all these source separation-based approaches. And so actually we have some small theoretical work even where we try to figure out what this multi-label classifier is doing when you have overlapping sounds. And hopefully I have later then a better explanation what is exactly going inside the DNA. And okay, like in speech processing, you can model a local temporal context by simply concatenate frame. range. And even longer term structure of sounds can be modeled with more advanced networks like BLSTMs that we have used. Okay, there's plenty of technical challenges that I wasn't really explaining here, but like, okay, robust classification is obvious. That's mostly what we are doing is it's a classification problem. But for example, if there is mismatch, you have some training data, but you want to apply your methods in some new environment. How do you adapt? In the case of speech, that's slightly easier because you expect that you develop speech recognizer in one using certain type of material and apply it on other. You expect that in the new environment there is some speech that you are recognizing. But in the case of acoustic events, then if you apply it on new environment, in the new environment then you may not know what kind of events there are. So and adaptation is more challenging. What is your target in the adaptation? And okay, similar to speech, I mean in speech language models help a lot. So what kind of language models we could use for sound events? Okay, there is a bunch of references here. You can find them from my webpage. And okay, there is plenty of people at TUT who have contributed to this work. I'd like to thank them all. And then, okay, about the challenge. So there is quite many research groups working on sound events, and but all the teams have a slightly different database. Most of the projects are more applied, so everybody has their own database, own goals, and it's that makes it slightly difficult to compare different methods, and in order to help making progress in this field, then we are organizing this IEEE AASP challenge on detection and classification of acoustic scenes and events next year. This is a continuation for the challenge that was organized 2 years ago. And we have there 4 tasks. So the first one is acoustic scene classification, which means you have an audio signal and you need to figure out from which context class the recording is from. So this is a classification problem. Then we have 2 tasks related to sound event detection, synthetic and real life. And the synthetic one uses sounds from an office environment, and there we have, in order to make this task easier to approach, we have there also isolated training material, also polyphonic training material, but sounds in isolation. And in the case of synthetic material, of course, we can get perfect ground truth. So, of course, this task is slightly easier in that sense. Then we have this real-life audio sound event detection tasks, which will use material similar to the one that I was showing, this CASA database. So we are going to make data like this publicly available for this challenge in a few months. And there is annotations of most common sound event classes present in the contexts that will be used. And okay, in this task we'll be using street and home context. And then there is domestic audio tagging, where the task is that you have given a 4-second audio segment, and you need to figure out which of the you need to give labels to this segment from a set of predefined labels. So it's also a classification problem. And so we are aiming to have the challenge open in January, and deadline for submissions perhaps around June. And then we are organizing a one-day workshop related to this challenge around September 2016, perhaps as a satellite for MLSP or USIP conferences. And there is the website of the challenge. You can find a link to that also from my webpage. Okay, thank you very much.
Are there questions? Brian?
You mentioned one limitation was that you don't believe your annotators are very accurate. I wondered if you had already done any spot checking on inner annotator agreement to see, if you used annotator A, what was annotator B's score, F score?
No, I haven't done that. I would very much like to do that. The problem is that the annotation is such time-consuming that we haven't yet had the same data annotated by multiple persons. But related to this task 4 of the challenge, domestic audio labeling. So then there are annotators from 3 persons. So Mark and Sasha over there know a bit more about that.
Another question? Yeah.
Hi. So yes, one of the challenges of audio event recognition is that there is a larger diversity of types of production processes and therefore types of sounds. Have you observed that that recognition rate that you get is homogeneous across all the sound classes, or some sounds are being better recognized than other sounds?
Obviously, we have measured the class-wise accuracies, but I don't recall right now anything specific. At least I think, of course, there is big difference in the amount of training data that you have. And I think that affects at least the scores a bit. But I don't recall anything specific about the acoustic characteristics of this.
Okay, so you think the amount of data has a larger effect than the type of acoustics? Okay.
Yes. One last question, Paris?
So I tend to think of deep networks as doing some kind of a mapping, right? Here's an input and you have to map it to that output. Which means that you won't be able to recognize a mixture of 2 sounds if those 2 sounds have never been seen in the training data.
That's about which I think we would like to have some theoretical results, hopefully, later. But yeah, I think, of course, you can do things like augmentation. You can mix your material, and I mean that's what we did actually in the case of BLSTMs, and that helps a bit.
And then as sort of an extra note to that, that also means that you have to train on multiple mixing ratios as well.
Yeah, but it seems that it might be possible to actually recognize combinations that are not present in your training data.
Okay.
We have some preliminary results about that.
Thanks. So it's time to thank Tuomas.
Thank you.
And we're moving to a coffee break. We're slightly late, so I suggest maybe we shorten the coffee break just a bit. Maybe let's try to restart it around 11:20. So coffee is going to be served over there, and there should be some food over there. Thank you.